Remember, this video is part of a video sequence converging the HYSYS simulation of the chemical distribution in toluene's hydroalkylation to produce benzene. A link is available below. The next thing we're going to do is to add and adjust and set to let HYSYS do the material balance for you inside the reactor. So we're going to use the provided information about the scale of the process. We're going to use the operating factor, and all of that information will help us to help the reactor calculate exactly how much of the feed do we need to meet the specification in the problem. We're going to add two functions or manipulators or mathematical manipulators to the simulation. The first one is an adjust and the second one is a set. So to do that, we're going to come here to manipulators and we're going to add an adjust. And here we're going to add it. I'm going to actually add it here in the bottoms because the adjust is going to end up being between the desired amount of product coming out of the reactor, right? This is the number that we know from the problem. And we're going to adjust the amount of the limiting reactant to meet that specification. And then automatically we're going to create add a set. So if I come here to set, the set will help us to, from the amount of toluene being calculated to meet the specification, we're going to keep set, right, the stoichiometry between toluene and hydrogen in order for us to, well, calculate everything that we need of the fresh raw materials. I recommend you to double click the adjust and then come here to the help and review the different parameters and how it works. Before I move on, what I'm gonna do is the amount of raw material that we need is going to be based on the amount of product produced. So for the adjust, we need to use the same units between the feed and the reactor and the exit of the reactor to be able to operate the adjust. So typically the product is specified in HYSYS using amount of mass per hour. So what we're going to do is make sure that the amount that we have here user specified, right, is the mass flow and not the molar flow, right? So it's user specified. So I'm going to come here, I'm going to delete this and I'm going to put 100. You can actually add the same amount that you had, or you can just go back again here to 100. And then I'm going to do the same thing here, right? Actually, I'm going to come here to the amount of molar flow that you need is 1.084. But honestly, what I'm just going to do is add 100 of the feed. Let me just do that. And I will let HYSYS to calculate that for me, so I don't worry about doing the calculations and letting the system have as many significant figures as possible in the iterations. Okay, so we did that. We put everything in terms of mass flow. So before I use the adjust, I'm going to actually use the set. So in the set, we will use the set. We will set, right, the amount of hydrogen based on the amount of toluene. In the statement, they tell us that it is okay. They tell us that it is okay that hydrogen is in excess. Typically, it is like that. That means that they're giving you a hint of what is the limiting reactant in the process. So here is going to be toluene. So what I'm going to do is double click this set. And notice that there's two things that you need to indicate. The first one is the target variable and the other one is the source. Once you're here, you can always come to the help. And in the help, you will be able to go through an overview of the different, what is the meaning of the set. Notice that the set is basically a linear equation where you have a dependent variable and an independent variable. So here, what we're going to have, we're going to allow the adjust to calculate the amount of toluene, and that will allow us to calculate the amount of hydrogen based on the stoichiometry or the amount of excess that we want to put. Right now, we're going to use a 1-to-1 ratio, and it also explains to you where are the properties and all that. Anyways, coming back here, okay, the target value will be the Y, right? What is the, here it will be the hydrogen. So we're going to come here to select the object. So the object could be a stream, it could be, a unit, whatever you have there on the diagram. Here I'm going to put hydrogen feed, and here I'm going to find the molar flow. I want to have the molar flow because I want to put a 1-to-1 stoichiometry, which is easier to recalculate the amount of mass because we know the stoichiometry, how much we need of the hydrogen at least, right, to make sure that it reacts. And automatically, because the units of the target variable is in molar flow, automatically the source will be molar flow too. So here we're gonna come Toluene feed. Notice that there's an inconsistency error. So this error was kind of like planned for you to see. Troubleshooting in HYSYS is a very important skill. So I wanted you to see and experience how this look. So a consistency error typically occur when you are over specifying. Here, you have the variable information. So here you have an inconsistency with the molar flow on the hydrogen feed because we are asking the set to calculate that for us. At the same time, we have a number already in place. So what we're gonna do, right? Notice here that we have a number added there and we're asking the set to do the calculation for us. The other thing that I want you to see is that automatically when you see these errors, this solver go on hold. So we're gonna deal with that in a moment. So I'm gonna come here. I'm gonna go to the hydrogen where I'm having the problem. I need to allow that mathematical manipulator to calculate the amount of hydrogen for us. So we're gonna come here and activate and notice that automatically the amount of hydrogen is calculated for us. I can come here, 1.085 and 1.085 as the molar flow for this. So the set is working. The next thing we're gonna do is to work with the parameters tab, and this is something that the students typically forget to do. So here you need to specify the multiplier. So automatically the multiplier here is 1. If you have a scope of work or a problem where they're telling you that hydrogen is in 30% excess or 50% in excess, so this is where you identify, right, the multiplier. Right now, we're saying that the ratio between the two is 1-to-1. So here you can add it, right? I'm gonna leave it 1. Notice here that it summarized the amount of the meaning of the linear equation. So right now we have exactly the same amount of toluene will be the amount of moles, right, per hour of the hydrogen. If you say that you have 5% more or 3% more or 5% more, automatically that will be calculated for us. But we're gonna leave it like this because we're gonna be having an excess hydrogen when we add the recycle later, and you can always come back here and modify it. The next thing we're gonna do is to work with the adjust. So we're gonna double click. You can come here to the help. I recommend you to review what the adjust means. Once again, basically the adjust, what it does, it varies the value of one stream variable, the independent variable, to meet the required value or specification, right, of the dependent variable in another stream or operation. So this can be on any type of object. It could be a stream or it could be a unit. And there's more information here for you to read. For the adjust, we have something that is called the adjust variable. And we have the target variable. So the adjusted variable in this particular case will refer to the toluene. We want to adjust the toluene for us to meet the target of the product that we want, okay? Remember that that amount was already calculated in the previous video, so we know how much we need after adjusting that for the operating factor. So I'm gonna come here to select in the toluene feed. I'm gonna find the mass flow. So I'm gonna just type flow. Okay, you can also adjust the molar flow, but typically you have to keep again the same units. So we calculated the mass flow for the target. So we're gonna keep it in terms of mass flow. It is not a problem, right? Because this will calculate the amount of toluene in the feed. And because we have a calculation of the molar flow, automatically the set will respond to that calculation. The target value or the target variable here will be S3. is the stream coming out of the reactor, which has the product. And then we're gonna get also flow. You're gonna scroll down and say, identify the master component flow to identify benzene out of all of the components that can be coming out of the reactor due to the side reactions also that we have there. Remember that the benzene is not the total mass flow, right? Because we have other components coming there. We need to specify the amount. So there are different ways to do this. We can add it, right, manually. Notice that automatically is pound per hour. This is a trick. It tells that you can go back and forth between the units, but it doesn't work like that. It does like an internal calculation, and I have never get it like the right amount. The amount that I'm specifying, it does like a weird calculation. So I typically specify if this is mass flow, if the target is mass flow, I'm making sure that the number I add here is already mass flow, and then automatically the adjusted value is calculated for me. So just be careful with this. You can also say that you have this located in another object, right? So you can also have a spreadsheet located on your process flow diagram, and you can call upon a cell on that spreadsheet, and that can be specified too. So here I know exactly how much I want. So if I think in the previous video we obtained around 180.8 pounds per year. Basically, if you convert that to pounds per hour, you end up having 26.42 pounds per hour. Notice that it's asking us to do maximum and minimum, and this could be weird, especially in the beginning when you don't know the boundaries of how much toluene in the feed you need to actually meet that target. So you need to kind of work out with trial and error until you found those boundaries. When time passes, you're gonna get used to this, and you may be able to predict, right, how much it's gonna be. So how we're gonna do this, right? We're gonna do it manually. So we don't want the adjust to be working. So you can always come here and ignore it. I'm gonna ignore it while I figure out the maximum and minimums. Okay, so I'm gonna come here to parameters, and I'm trying to determine the minimum and maximum between the benzene, right? The boundaries, right, for the benzene and the toluene that I need in the system. So let's play with that. For me, the easiest way to do this is by adding tables to my diagram. So I'm gonna decrease this a little bit. Let me just organize this a little bit. And I'm gonna click the stream, show table. You can show multiple things, right? Right now, the only thing that I want to look at is the mass flow. So I'm gonna remove variables. And you can come here to flow. Component mass flow, because I'm on the toluene stream, I just want toluene. Technically, you can put pure, like just the total mass flow, because in that stream, you only have toluene coming in right now. Okay. Then the next thing I want to do is keep track of the hydrogen too, to check that my well, you don't need the hydrogen. You're just comparing the toluene and the benzene. So let me just focus with the toluene. You can do the same thing. The benzene. Remove, 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 add. Here is benzene. Notice that right now, we have 100 pounds per hour, and that it is producing 62.3 pounds per hour. Notice that that is not what we want, right? We want around 20,000 pounds per hour of the benzene to be produced. So what we're gonna do is slowly go from 100 to a number where we can see that we're slightly over the amount of benzene that we need. And that will allow us to set the adjust with the appropriate boundaries. So I'm going to go and do 500. Notice that I get 300 pounds per hour of benzene. So we're still low in the low end. I'm just going to do 2000. Notice that we're still too low in the 1200s, I'm sorry. And then you can do 3000 of toluene. We're still under 10,000. We're still under. You can do 20. You may say why the professor is going so slow. Well, is that this simulation software has a tendency to crash sometimes, so it can go overboard in terms of the number of iterations. That's another parameter that you can manipulate in your simulation, but we're not playing with that right now, so you don't want to exceed the number of iterations, so I go very slowly. So let me do 4000. Notice that we actually went over. So let me see if I can reduce that between 30,000 and 4,000. So I'm just going to do 35,000. And notice that we're barely over, right, by 1,000. Our target was 20,642 pounds of benzene. So right now, if we say that the upper limit boundary of the toluene is 35, we're going to be able to allow the adjust to calculate a number that is within those parameters, okay? So I'm going to come here, close it. Actually, I'm just going to get back to 100. Just to allow the adjust to do the iterations for us. So here the maximum we set, it was 35,000. Okay. Remember that the adjust is ignored. So if it's not doing something, if you click here and it's not working, it may be that the solver is off. So I'm going to just click here. It is asking me for a minimum, so I'm just going to add 100 because this is where my initial amount of toluene is right now. When you click enter, I think this pops up, so I just bring it here so you can see it. So here they're telling you that you wish to continue to another number of iterations. You can click yes, and if you have between the 10 more iterations, you may be able to converge. But if you don't know, if you don't want to if you do it multiple times and it's like forever, you can just say no, and then come here and increase to a high number, 100, 200. I'm just gonna put 500 just because. Okay, I'm gonna reset. So 500 iterations and we're still over. So here I'm just going to click yes to see if I'm lucky. Maybe I need to add a higher number, and no. Okay, so 500, more than 500 iterations it actually took us to do this. And if you come here, it was 650 iterations that you needed to converge this. So sometimes you don't know, you just have to kind of guess. You can start with 200, 100, and play with that number. So notice that the target amount that we needed was 20,642 pounds per hour, but we're not there yet. So we do have an issue, right? What is going on? So basically, the problem that we have is that we have to play with the tolerance and the step size for this. So let me come here and quickly show you in the help, right, what that means. So the tolerance sets the absolute error. In other words, the maximum difference between the target variable and the target value. So we want that absolute error to become smaller and smaller, right? So the target and the calculated value become very close. The other thing that we need to play with is the step size. which is the initial step size employed until the solution is bracket. So if you have a high step size, that means that if you have to be in, it's like the significant figures, right? Where you round up, right? So the smaller the step size, the closer, right? And the more accuracy that particular number will have with respect of the target value. I'm gonna close here, come back to my simulation. So let's start doing that. So I'm gonna put this a little bit up so you can see here the changes in the amount of benzene. Remember, our target is 20,642 pounds per hour. So we want to make this number closer as possible. So I'm just gonna start doing this. So let's set the tolerance initially to 150. Notice that the amount of benzene slightly increase, getting closer to our target. I'm gonna do the tolerance to 100. Notice that the number becomes closer also to 2642. I'm just gonna do 50. There's an increase, right? Very close to. Let me do 25. Okay. There's a slight increase. Let me do 20. Also slightly increase. You can also increase that step size. I'm just gonna do it 20. Okay. And then I'm just gonna do, let me do 10. 10. And I'm gonna do 1. Okay. And notice that we reached the target amount. Okay, so students, forget to do this. If you're not meeting the specifications, that means that, the calculated value of the raw material is underspecified. So make sure that you go through this process. Save it. I want to point out that I want you to notice, right, that these tolerances are so small that they may become a problem in the future, and you can relax them back again, right? If you see that the simulation is not converging. Adjust can serve a purpose. So my advice is when you finish something like this, you take a snapshot of the workbook and save it. The last thing I will recommend you to do is to save this file with a timestamp, or maybe with a label that says reactor's initial setup, right? And the reason is that as you progress on your simulations, you will be changing the PFD. So if you want to go back and document the different stages of your design, you may want to keep track of the different changes and the different workbooks that you have. You can always put a timestamp. This is what I did just here. If you see at my name for my file, you can change it and say, for example, PDF 1 reactor set or something like that with the last day that it was used. And keeping the files organized is a very important thing, especially when you're working with another team of engineers in the project.